Hello and welcome to the third and final module of Lecture 1 of EE635 Applied Linear Algebra. So far we have been looking at various examples of the situations where we are required to solve for equations like Ax equal to B, where A is a known matrix, B is a known vector, and X is an unknown vector. We have to solve for X. So far we have seen mostly two such examples, namely one where we have an electrical network, right? It turns out that solving for the voltages and currents at various branches or at various nodes turns out to be finally solving Ax equal to B, right? And then there's this electrostatic equation, which actually is a partial difference equation, yeah? The so-called Laplace's equation. But then if you try and solve it computationally, numerically, uh, using the finite difference method, it turns out to be, once again, an equation like Ax equal to B. Now we will see one more such example, which is once again quite far away from these two. Yeah, but ultimately it will be an equation of the type Ax equal to B. Yeah, namely the discrete Fourier transform. Okay, right. So let us see. Okay. Now, so what do we do in discrete Fourier transform? So discrete Fourier transform involves a discrete time sequence. Suppose this is the time axis, but this has been discretized. So we have a discrete signal of finite duration. They are represented by these impulses. So it's basically an impulse train, but of finite size, finite length rather. This is my finite length discrete signal, right? What I do is that I say that the strength of these impulses are given by the numbers, the real numbers x0, x1, x2, x3 dot 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 xn minus 2 and xn minus 1. So it's a length n, length capital N sequence. The way to write this, the way to represent this is capital X is equal to this sequence of x0, x1, x2 dot 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 up to xn minus 1. So this is my discrete time signal, right? So if I just go ahead and find out its Fourier transform, then I know that this is given by x check omega is nothing but by definition integration from minus infinity to plus infinity e to the power minus j omega t, and then this signal xt dt. Now what is xt? Xt is this impulse train. So then this turns out to be minus infinity to infinity e to the power minus j omega t. And then I have summation small n going from 0 to capital N minus 1 xn delta t minus n tau, where this is, this length is tau. So this point is 0, this point is tau, this point is 2 tau. Yeah, this is tau, this is 2 tau, this is 3 tau, and so on. Right? And dt, of course. How can I forget dt? Yeah. Then, if I carry out this integral by the formula of integration with Dirac delta impulses, we know that finally what we're going to get here is this sum, this summation n going from 0 to n minus 1 xn e to the power minus j omega n tau, right? So this is the sum that we get. So notice that this x check omega, the Fourier transform, happens to be a finite sum of exponential trajectories, yeah, with minus j appearing here, which means these are actually sinusoidal cosinusoidal trajectories from Euler's formula. Okay, right. Now, now what we see here is this as a function of omega. So x as a function of x check as a function of omega. In order for me to know this x check omega, I actually don't need to know it at all the frequencies omega, all the values of omega. Why do I say this? Because notice essentially that this is actually exponential signals of which I know these frequencies. Yeah, remember that this is the independent variable now. The frequencies are here. So frequency is tau, 2 tau. In fact, 0 also is there. So in order for me to know this whole x check omega, all I need to know is xn values, right? But how, and there are how many capital N number of such xn values, but how can I know these xn values, the amplitudes, yeah, by evaluating this x check omega at different omegas? You're getting my point, no? What I'm trying to say here is that for this x check omega, is it possible for me to know this x check omega for all omega by knowing x check omega only at finitely many omega values? Yeah, and in fact, it is true. You can go ahead and check that if I now define x check a sequence of x0 check, x1 check, dot up to xn minus 1 check, where each of these checks are defined as x check k is by definition summation x n e to the power minus j 2 pi by n into k into small n, where n goes from 0 to capital N minus 1. If x check is defined like this, yeah, then you know that if I know this x check k, if I know this, I actually know all of this. Because from here, I will be able to find out xn. Indeed, for example, suppose we have a situation when n is just equal to 2. So in that case, I have, so this is for example, n equal to 2 would mean my sequence x is just x0 and x1. All right. So in this situation, I will have x check omega given by x0 plus x1 e to the power minus j omega tau. In that case, if I try and find out, okay, x naught check, from the formula x0 check would be x0 plus, so put k equal to, so the summation goes from n equal to 0 to 1, right? This is what this is. And then when k is equal to 0, this part is also equal to 0. So therefore this will be just x1. And of course, x1 check will then be, let us once again, so let me write down the formula. N equal to 0 to 1, x0, xn e to the power minus j 2 pi by capital N, in this case is 2, k into n, k in this case is equal to 1. So this is nothing but x0, yeah, plus x1 e to the power minus j, this cancels out, j pi, k is 1 and n is also 1, e to the power minus j pi. So then we have this two information, x0 check, x1 check. X0 check is this one, x1 check is this one. So if I know x0 check and x1 check, I actually know what is x0 and x1 are, because I can write down this equation that 1, 1, 1 e to the power minus j pi x0, x1 is equal to x0 check and x1 check. So if I know this, I already know this, I can find out this one by try and figuring out what this guy would be. Okay. Yeah. In fact, we can go ahead and write what this e to the power minus j pi would be. What is e to the power minus j pi? This is equal to cos minus pi. Okay, cos pi is fine. Just write cos. Yeah, we can just write cos pi minus j sine pi. This is from Euler's formula. Sine pi is 0. Cos pi is, I think, minus 1. Yeah, if I'm not mistaken. Yeah, 1, 0, minus. Yeah, right. Cos pi is minus 1. So then this matrix is nothing but 1, 1, 1, minus 1, which is actually invertible. Right? So this turns out to be a linear equation. In general, as I said before, x check now is given by x0 check, x1 check, dot 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 up to xn minus 1 check. Yeah, this value in whatever, okay, if I call x check as a vector like this, x0 check, x1 check, dot 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 xn minus 1 check. If I call this as a vector, similarly, if I call this guy also as a vector, the time series, the time sequence, then what happens is x check is given by this matrix F into X, and this F is the discrete Fourier transform matrix. This goes to you as a homework, that find out F. So you see, discrete Fourier transform also turns out to be of an equation like this. So in general, what happens is, if I know discrete Fourier transform of a signal, and I know the Fourier transform matrix, then I can find out the time domain signal. If I know the time domain signal, from there I can find out the discrete Fourier transform, right? This is the direct problem, obtaining x check from x, and this is the reverse problem. The reverse problem is the one that we are interested in. Yeah. Okay. So as an aside, it should also be interesting to mention the following. You see, when I said that for the Fourier transform, I have x check omega, this is what I should know. But then I can afford to not know x check omega for all omega. This should remind you something about data compression, right? For example, suppose one would have to send some signal which is of sinusoid type. Yeah, some sinusoidal signal, suppose one would have to send from one place to another through some, through some channel. One may think that, okay, this is a signal, so at every time the signal has some value, so I will send all these values, yeah, in time. Then chances are that those time domain data, those data packets or whatever, those information may get lost because of all sorts of reasons. Because of the, there could be problems with the channel, there could be problems with the environment, there could be all sorts of things by which these data that you're transmitting over a channel would be lost. Yeah, so this is actually very expensive. Whereas on the other hand, for a sinusoidal signal, if you send only the amplitude of the signal and the frequency of the signal and the phase difference of the signal, just these three informations, then the receiver that receives these signals with the information that this is actually a sinusoidal signal, the receiver can reconstruct the actual signal that was supposed to be transmitted from the information that has been sent, right? Yeah, this is how data is compressed. So for a large mixture, right, if you take its Fourier transform and send only the small frequency components like this, yeah, then the receiver will be able to reconstruct the signal to a reasonable degree of faithfulness, yeah, without actually going through all the all the information, without actually getting all the information, as in the time domain signal. The same thing happens with image compression also, because in image compression, the bitmap image contains the pixel grayscale values or the pixel RGB values for every pixel. But in order for us to recognize some high definition picture, we actually don't need to have all those grayscale values or RGB values at every pixel. Instead, we can take a discrete Fourier transform and store only the small frequency components which our eyes anyway can discern. Yeah, those very high frequency contents, very high contrast contents, our eyes even may not even be able to discern, may not even be able to distinguish between. So therefore, it always makes sense to do this kind of transform and send only those information that is required. Similarly here, this x check omega is what I should know. From Fourier transform theory, I know that I need to know x check omega in order to reconstruct x. But here, because it's a discrete signal, there are only these finitely many exponential functions which are present in the discrete Fourier transform, discrete time Fourier transform. Therefore, I can afford to know x check omega only at finitely many omegas. And at what omegas should we know them? Well, I just look at the fundamental component here, as in this case. So here the fundamental component will be 2 pi by 2 pi by uh, 2 pi by tau, right? 2 pi by tau. That's the fundamental component. And from that fundamental component, I just partition that into finitely many, into in fact n equally spaced equally spaced such points, and at those points I find out omega, and from there I get my x check vector. Okay. All right. So let me remind you, this goes to you as a homework to find out this matrix F. Yeah. So you see, we have seen these three quite varied situations where we have been able to see that, finally the problem boils down to solving something like ax equal to b. So that is how ubiquitous ax equal to b kind of equations really are. And that is why it makes ample sense to study how to solve these equations. And then to also realize, to also, fortify ourselves with these tools, which would allow us not only to understand and solve ax equal to b type equations, but also should empower us with the ability to recognize a problem where such ax equal to b, finally the problem will boil down to ax equal to b. So far we have seen these three cases. It does not mean that these three are the only ones. And later on when you do your research in your problem, you will find out that there's something which people may not have been able to solve, but then you'll realize, okay, actually this thing is nothing but ax equal to b. Yeah. So we will try to empower you, try to provide you with the intuitions, with the ideas, so that you will also be able to figure out that this is actually ax equal to b problem. Yeah, that is where the abstraction comes in. I'll give you one very quick example, which is not new actually, but something which is so stupendously, not clear that it would be actually Ax equal to B kind of equations, but ultimately it will turn out to be an Ax equal to B equation. And the idea and the goal is that, when you're done with this course, you should also be able to make connections like this. So I'll give you that example. I'll tell you that example. That example is the following. So um, suppose you are inside a room like this. You are here. Holding up a binocular. And here, there's a fly, right? And you have traced out the fly's flight path. You have figured out this location, all these coordinates you have found out. You want to predict its next position based on these positions that you have figured out, such that this prediction would be as close as possible to what is going to happen. Yeah, sounds weird, right? How is that even possible? But it turns out that if we make some reasonable assumptions, we actually would be able to figure out that um, would be able to figure out how one can predict the fly's next position based on these uh, previous measurements. Yeah, this is known as a Wiener filter, and we'll see in one of the subsequent lectures that Wiener filter actually also turns out to be ultimately solving Ax equal to B. Yeah, with this note, let me put an end to today's lecture number 1. We'll meet once again in lecture number 2, and of course we'll keep meeting on our interactive sessions, which are going to happen on Mondays and Thursdays from 5:30 p.m. to 6:55 p.m. Okay, stay tuned for all the details on Google Classroom as well as on Moodle. Okay, keep checking your mails, and of course, stay safe, stay healthy, take care of yourselves. Okay, bye bye.